In this experiment, our objective is to study the transient response of LCR circuits. Like if you apply a sudden step, like a transition from say 0 to 5 volt to a RC circuit or LC circuit or LCR circuit, that means a resistor and capacitor in series, or a resistor and inductor in series, or all the three elements in series. And then we will study the voltage waveforms across the capacitor, plot them and try to extract the value of inductance and capacitance using the theoretical equations. First we will explore the RC circuit. So, here the features of the box we are going to use is, one is we will use this terminal called OD1, that is a digital output that can be set to 0 or 5 volt very quickly under software control. And then we will use our A1, that is a voltage measurement terminal. So, the capacitor will be connected from A1 to ground. You can see the capacitor is going to be connected to A1 to ground, and we will connect a resistor from OD1. So, here you can see the resistor. So, you can see the connections here. A resistor is going from OD1 to A1, and from A1 to ground we have the capacitor. So, from experiments menu, let us choose the RC circuit. So, we have the pop-up window here, and you can see we also have the circuit diagram here, say resistor from OD1 to A1 and a 1 microfarad capacitor from A1 to ground. So, what we are going to do is we suddenly apply a voltage across on this resistor at the point OD1 and see how the voltage changes after that at A1, that means across the capacitor. For that, just press on the button here 0 to 5 volt step. You see this is how the voltage changed, and instead of that, now let us give a 5 to 0 volt step. Here you can see the discharge curve of the capacitor, and as you can see this is happening exponentially. That means, a RC circuit, when it charges or discharges, the voltage across the capacitor changes in an exponential manner. Now, fitting this curve with the equation of the RC discharge will give us the time constant RC. So, we can say calculate RC. It says it is 1 millisecond, that means 1 kilo ohm in 1 microfarad is 1 millisecond. So, you can use this experiment to measure the value of a capacitor. So, all you have to do is use a resistance of known value and extract the RC time constant, the product of RC, from the graph. So, we have seen how the capacitor behaves when you give a voltage step through a resistor. Now, we will try to do the same for the inductor now. For the inductor, we will use this coil which is having 3000 turns of copper wire. So, we will simply replace this capacitor with our inductor. So, you can see the connections here. This step will be given here through a 1 k resistor to this inductor, and we will measure the voltage at this point. And now, coming to the screen, from experiments menu you start the RL circuit. So, the pop-up window is here, and give a 0 to 5 volt step. You can see that this is how the voltage across the inductor is changing. If you give a 0 to 5, see there is something slightly different here. When you give a 0 to 5 volt step, the voltage across the inductor is starting already at 5 volt, then start coming down, but it does not reach 0. That is because the inductor also has a finite resistance. Now, let us give a 5 to 0 volt step. That means, we are keeping the point OD1 at 5 volt and suddenly taking it to 0. this gives a very interesting result. We gave a step here say 5 to 0 volt, but the voltage across the inductor suddenly went to something like -3. We did not apply a negative voltage, but it went to, so that it generated a negative voltage. This is due to the phenomena called the back EMF, and after that starts discharging through the resistor, and you have this discharge curve like this. Now, we can calculate the R by L value by fitting this graph with the exponential equation, and it says after the measurement the L by R is 0.085 millisecond, and it also measures the resistance of the inductor, it is around 603 ohms, and the inductance is 136.5 millihenry. That means, this experiment we learn about the nature of transient response of an LC circuit. It also can be used as a tool for measuring inductance. Suppose you wind a coil, and if you want to measure the inductance, that can be measured using this way. So, we have seen the transient response of RC circuit, that is the resistor and capacitor in series, and also the RL circuit. And we can see that the RC circuit, the response is fairly simple, but the RL circuit showed the phenomenon of back EMF. But in both cases, the voltage increase or decrease in a monotonous manner, it does not oscillate. Now, we will connect both inductor and capacitor together and see how the response is behaving. So, let us connect L and C together, like we will remove the resistor. So, our circuit connection will be from OD1 we are connecting the coil to A1, and then we will use a small capacitor. So, we will use a 0.1 micro capacitor, 0.1 microfarad instead of the 1 microfarad. That will explain why we are doing it. So, we have made our connections. So, you can see here we have a capacitor and an inductor, and remember the resistance is already built in, because inductor itself has a resistance of around 600 ohms. So, to study the response, let us have a look at this screen again. So, choose the program RLC discharge. Here we have the pop-up window, and we give a 5 to 0 volt step. So, it shows something like this, it comes and goes to negative and trying to build up. So, let us change the time scale a little bit, repeat it. You can see the voltage from 5 to 0 volt step when we gave like this, the voltage across the capacitor is going like this, it just comes down, then does a couple of oscillations and it dies down. So, this is the response of an LC circuit, basically an RLC circuit, because the resistor is always there. Now, these oscillations, even though it is a couple of cycles, we can find out the frequency. Press on this fit, it says the resonant frequency is 1.3 kilohertz and the damping factor is 0.309. In fact, you can verify this by comparing with the theoretical value, that is 1 by 2 pi square root of LC. Now, let us try to explore different cases, like if you increase the resistance or increase the capacitance, this oscillatory nature will vanish, because this is oscillating because the circuit under present condition it is what is called the underdamped case. So, to increase the damping, we can put one more series resistance and see how this behaves. So, let us put one more resistance in series. So, we are taking a 3 kilo ohm resistor and putting that in series with the coil. So, you can see that there is one more resistor added here, then again on the screen do the response 0 to 5 volt. Now, you can see it does not oscillate, it has now become a sort of overdamped case. Now, there is no question of resonant frequency now. So, by adjusting the value of resistance, you can make it underdamped or overdamped, but also the ratio of the capacitance and inductance, that also matters. Probably what we can do is we will remove this 3 kilo ohm resistor, go back to our original case and change the capacitor. Like I remove the resistor and instead of our 0.1 micro we will put a 1 microfarad. Let us go to the screen and do the measurement again. We can see that this also does not oscillate, it is also either over damped or critically damped from the look of it. So, that means the nature of this voltage depends on the ratio of the capacitance inductance, that is the C by L value, and also the resistance in the circuit. It is possible to do the experiment using a wide range of capacitive inductor values and verify the measured resonant frequency with the theoretical value. So, now we have completed the measurements. We have seen the cases of RC, I mean resistance and the capacitor alone, resistance and inductor alone. Both cases we have the monotonous response of voltage across the capacitor, and then we tried the inductor and capacitor together and got the oscillatory response also. So, this concludes the RLC circuit, the transient response of RLC circuit.